Areva, your hand is up. What's your secret?
Yeah, please. What about the heat?
Oh, heat. We started. We'll continue from um our meetings next week.
Okay.
We have not dropped it. This was a deficit on on optics, light, convex, refraction, blah blah blah. Okay, so I'm trying to make up for. I think you have to pardon me. I still experience the coughing thing, so pardon me. So we'll continue with heat. Please, our next meeting is changed from Monday to Tuesday. I'll update it on the platform. All right. So if we've not shelved it, we'll continue with that. So optical instruments and enable us to see the aid or optical instruments
Yes.
aid vision. So let's discuss some examples of optical instruments. What are some of the instruments that aid vision or viewing? Can you share with me examples of some optical instruments? Irrevoir,
These glasses like spectacles.
glasses, they aid viewing, but we wouldn't consider them seriously as optical instruments. You understand why? Michelle,
Mr. Edward, please, is microscope, but
Michelle, is it a question or an answer?
please is an answer.
Okay, then microscope is parts. More views, more examples. A river again.
A periscope.
Periscope aids viewing. Okay. The gentlemen speak. Oh, hey, let me attend to them. Calvin. Calvin Kweku. Calvin. Give us one example of an optical instrument. Calvin.
Sir, please, binoculars.
Yes, binoculars are optical instruments. And Kweku, lastly, Isaac. Okay, Isaac. Isaac Carter. Oh.
Yes, sir.
An example of an optical instrument. Lastly, telescope, the astronomical telescope. Okay. Now, how do they aid vision or viewing? You see, no matter how big or small your eyes can be, you cannot see an euglena, amoeba, spirogyra, name them. No matter how big your eyes can be, you can't see them. But there is an instrument which can be used to still see these microorganisms. We cannot see bacteria, neither can we see viruses, no matter how good your eyes can be. But we can still have an instrument to do that. So with instruments, whether your eyes have defect or not, with optical instruments, whether your eyes has no defect, you are limited in viewing certain organisms or seeing certain organisms. But the optical instrument can bear you out in that situation. Now, Erefa, you talked about glasses, which in my view is not considered as though it's viewing, but it's not considered as optical instrument because you see, for glasses, whoever goes for glasses have a certain defect on the eye or of the eye. Then they look at the nature of the defect and then prescribe glasses to correct it. Okay, so the glasses is actually used to correct eye defects. I've not seen somebody who has no defect and goes for this medicated glasses. No. But with optical instruments, so you see, before they prescribe glasses for you, you will be called and your eye problem will be tested, out of which that recommendation will be given to your problem. But for optical instruments such as microscope, telescope, the magnifier, nobody will call you to test your eye before it is done. Okay, so with that, no matter how good your eyes is, we are limited in viewing microorganisms, and that is when microorganisms or objects that are very far. So that is when optical instruments bails us out or comes in to aid viewing. Please, is that okay? Is that okay?
Yes, please.
Okay. All right. So how do optical instruments aid viewing? You see, our eyes is such that, do you know, we see better when an object is far away from us. So ideally, the eyes are designed to see even from infinity. Or see, hey, yes, okay, but the eyes have no problem seeing objects at infinity, at far distances. This is because no matter the distance, the eyeball can adjust the focal length. You see, our eyes are converging lenses or convex lenses. Okay, so we have this natural lens within our eye. Okay, now the eye is designed in such a way that no matter how far an object is, the focal length of the lens can be adjusted in order to bring objects into focus. And this is what is termed as accommodation. Okay, so accommodation of the eye is the process of adjusting the focal length of the eye in order to bring objects into focus. Please let me take this call and get back to you. Okay, it's a very important call. Back from commercial break. So accommodation of the eye is the process of adjusting the focal length of the eye in order to bring objects to focus. Okay. So our eyes goes through what is termed as accommodation. That is by adjusting the focal length of the eye in order to bring objects into focus. And the eye, okay, the human eye does it very well goes through the process of accommodation very well when the object is far. Okay. Now, so when the object is far, the eye focal length can be adjusted to bring it. However, when the object draws nearer to us, there is a limit, a point where accommodation, okay, can be done. Beyond that point, the eye cannot go through this process of accommodation in order to bring object to focus. So the eye does it better when the object is far at infinity. Okay. Now, the size of objects we see is as a result of an angle subtended on the eyes, on the retina of the eye. I will explain everything to you. The size of object we see is as a result of the value or the angle which is subtended on the retina of the eye. When the angle subtended on the eye is large, the object will be seen as large. When the angle subtended on the eye is small, the object will be seen as small. Now we cannot see so very well from a distance, even though the eye goes through accommodation, because when the object is far, the angle subtended on the eye is very, very small. Okay, and the size of object you see is directly proportional to the angle which is subtended on the eye. Practically, if you are you happen to be seeing people at a very far distance, a lot of people, but the distance between you and the people very, very far, you can hardly distinguish between a tall person and a short person, even though you can clearly see those people. Please, are you following what I'm saying? If you are standing on a story building, maybe the ground floor. Leonard, please mute yourself. Leonard, if you are standing on a story building and you see a lot of people at a distance, seeing those people, you can hardly identify a tall person from the crowd. It's because of the distance. However, if one tall person within them draws nearer to you, as the person draws nearer to you, that is when you can identify that, oh, this person is tall. But when they are very far, looking at the people, it's always as if they have the same height. Okay, this implies that the size of objects, or yes, items we see is directly proportional to the angle which is created or subtended on our eyes. We cannot see bacteria because the angle which is subtended on the eye is very, very small. So we cannot appreciate the size of bacteria. Let me explain this with a diagram. This is the eyeball. The foam of the eye is here. That's the retina. Retina is like a screen which captures the image formed on the eye. Let's draw a line so this thing I've drawn is the eyeball. We are considering the same objects being seen by the eye. However, we are going to vary the position of the objects. So if the object is here, the angle subtended by the object on the eye will be this. So the angle which is subtended on the eye per the height of the object is this. This angle is equal to vertical opposite. So this is theta. And so this will produce an image like this on the eye. So on the eye, this will be the image formed. Let's have the same objects moved forward and see the visual, angle subtended on the eye. The same height. The same height, but we are varying the object's position. Earlier it was far, now it is here. And the angle subtended by the object on the eye is this. So you realize that this time around, this is the whole angle subtended on the eye. Okay. Vertical opposite angles are equal. So with this angle, look at the height of the image formed on the retina. Now, when the object moves closer, it would subtend a very large angle. This is the angle. Now, the size of image we see. So in the first case, A, B, C. In C, this is the angle. When the object is very far, because it subtends small angle, you see the object to be small. So the image formed on your eye, and that is what you see, what the brain interprets. You also see it to be smaller because the angle subtended on the eye is small. When the object comes forward to B, the angle subtended is this. Because the angle is large, the image seen would also be large. And so the size of objects we see is directly proportional to the size, to the angle subtended on the eye. This angle, subtended angle, is known as visual angle. This is known as visual angle. So, in brief, The visual angle determines the size of objects we see. So that is the reason why when an object is far, okay, you can hardly appreciate the size. Hence, explanation to the fact that when a tall person is very far, you can decipher the tallness or the height of the person. Class, please, are you okay? Class, are you fine?
Yes, please. Yes, please.
So, an object, even though our eyes can go through a process of accommodation better when the object is far. But when the object is far, the angle which is the visual angle is very, very small. And so we'll see the object to be very, very small. Okay. A tall tree at a distance is seen as short because of the visual angle. Okay. So, as an object draws nearer to us, we appreciate the size and then the height of the object due to the fact that it subtends a very large angle on the retina of the eye. Now, the images formed by our eyes is actually inverted. So, on the retina of the eye, the image of the laptop on the retina on the eye is inverted. If you are in front of me, or if I look at you, the actual image which is formed on the retina of the eye, your head is turned upside down, your legs are up. But it is the brain that gives the interpretation of what the retina picks for it to look like upright. But on the retina, images are turned upside down. They are inverted. That is why in drawing the images, you see the images are turned upside down. That is what happens on the retina. Please, is there any question before I continue? So with Mamia.
Please, if your eye is what is seeing it, and the retina is sending, the image is inverted on the retina, and it's sent to the brain. The brain is not the one that brought the image. So how is he able to tell that it's not supposed to be upside down?
There are optic nerves connected. You see, our body is like houses connected to electrical systems. From the toe to the head, there are nerves connecting our body to the brain. The brain is what gives interpretation to every activity of the body. So yes, the image of you captured on the retina is inverted, but messages or impulses are sent to the brain to give it an interpretation. So these nerves, which sends information from the retina to the brain, is interpreted so that you, the observer, will see whatever as upright. All right.
Yes, please.
So
Thank
the brain
you.
actually does the interpretation of activities. But on the retina, Mameya, your head is turning upside down on my retina. Okay. All right. So as objects draws nearer to the eye, the visual angle is enlarged so that the object is seen better. Okay, if it's a small object, imagine somebody holding a cockroach and asking you to examine at a distance, maybe 1 kilometer. I mean, you cannot even determine exactly whatever is in the person's hand. But as the person draws nearer to you, you would then be appreciating the size and then the parts of whatever the person holds better. This is because as object draws nearer to you, the visual angle subtended on the eye increases. And because the size is directly proportional to the angle, you also appreciate the thing better. However, when the thing comes to you, there is a limit where there can be a clearer view of the object, even though we see better when the object draws nearer to us. But there is a limit. Beyond that limit, you cannot see clearly. Pick a book or whatever is in front of you. Okay, open a page. Take it far. Okay, or let your somebody, your sister, hold it at a distance. Try reading, and let your sister gradually bring the book nearer to you. There would be a point where there will be difficulty in whatever you are seeing. There will be a point where whatever the page you are reading would either be blurry. You wouldn't see it so well. Okay, so hold a book, your notebook right now, send it far, try and read, and then bring it towards you gradually. Gradually. There will be a point where you realize that reading becomes difficult. Please, I want you to do the exercise or the demonstration now. Pick your book, take it far first, as I'm doing. Take it very far, and then try reading from that distance. Then bring it towards closer to your eye gradually. Gradually. There will be a point where reading of the same text becomes difficult. Start work, do it, and then I'll pick information from. So start work. Mamiya, Frida, Kelvin, and the rest
Sir,
of you. Start work.
sir,
Uh-huh.
should we use a book that has small like writings or something?
Yes, it can be an image, writing, or anything. Just pick it. Take it far first and try. If it's a test, try reading. If it's an image, try viewing the image, and then bring the same thing closer to your eye and see if we want to determine if there will be a point where the reading or the drawing becomes indistinct, not so clear. Are you doing it? Are you doing it? Mamiya.
Yes, please.
Let me, whilst you are going through the activity, let me take our attendance, okay? So a minute or two, I'll get back to you. Okay, back to you. Class, did you identify a point where reading becomes difficult? Hello, did you identify a point where Mamia?
Please, in the beginning, I couldn't see the letters well. They were just looking like weird, small shapes.
So, you see, when it was far, how was the reading like?
When it was far, I couldn't see the letters, but I was able to see the image.
And did you feel that discomfort with
Yes.
your
Yes.
let me get the experience of somebody else. Yes. What of you? Mamia has shared with us what she felt. What about
I really didn't see anything. No.
Come again?
When it was far, when it was close, I didn't see anything.
No, you should. You see, the point is that if the object is far, reading is easy. Okay, even though if it's so far, there wouldn't be the letters or the text wouldn't be clear, but you feel comfortable looking at the text. Now, when it draws closer to you, okay, even though the visual angle is increased, but there will be a point where the reading becomes so diffuse, blurry, the text. You wouldn't see the text so well. Okay. So, and you see, for normal eyes, this distance, for normal eye, averagely, this distance where we can read clearly is roughly about 25 centimeters from the eye. So if you measure about 25 centimeters from the eye level, okay, this is my eye. If you measure about 25 centimeters, for teens, yours will be around 18, okay, but 25, 20, 18 averagely, this point where reading is clear, beyond it is not clear or indistinct, is always about 25 centimeters from the eye, your eye level. So when you measure 25 centimeters from your eye, that is the point where reading becomes clearer. Anything less than that, reading becomes a bit difficult. And this point is what is termed as the least distance of distinct vision. The opticians term this as LDDV or plus D. The least distance of distinct vision where reading is clear enough is always about 25 centimeters averagely from our eye, from the eye level. Now, this least distance of distinct vision actually increases with age. As you grow, you realize that your least distance of distinct vision will be receding or going far. So from 30, 40, you realize that it will be about 30, 35 from your eye level. And this explains the reason why old people, when they are reading newspaper, you realize that the newspaper will be at an arm length. The newspaper will be somewhere, okay, arm length, and then they will be reading, because as they grow, this point recedes or increases. And so where they can read clearly, they need to take the paper beyond this distance. Please, I don't know if you've seen old people reading newspaper at arm length before. Have you made that observation? Hello?
Yes, please.
It is because their near point or LDDV has gone far. So before they can read clearly, they need to take the test far from their eye before they can read. It's just because their least distance of distinct vision has receded. The average normal eye must be 25, at least 25, but as you grow, it recedes or increases with age. Me, for instance, I used to read very well when it is close. Now, because I'm 62, I've seen that changes. Is that okay? So that is what we mean by the LDDV, or the least distance of distinct vision, also known as the near point. Near point. Near point. And averagely, I said the normal human eye is about 25 centimeters from the eye. Please, is there any question? Is there any question? Mamiya, Julian, is there any question?
No, sir.
Okay, so let's write something. Let's quickly put down some information. I wish teaching this and then having you students around for a better demonstration. So the optical instrument, please put it down, okay? Write it in order to save time so we can go on. Optical instruments are used to assist the eye in viewing an object. Optical instruments are used to assist the eye in viewing an object. So we made mention of some examples of optical instruments: binoculars, the microscope, the magnifying hand lens, and then the telescopes. Can I continue? Can I continue?
Yes.
Our eye lens has a power to adjust. Our eye lens has a power to adjust its focal length. It has the power to adjust its focal length to see nearer objects. To see nearer objects. This process of adjusting focal length is called accommodation. I earlier told you about it. The process of adjusting the focal length is called accommodation. However, if the object is brought too close to the eye, the focal length cannot be adjusted. So this process of accommodation can be done easily when the object is far. Now, when the object is brought too close to the eye, this adjustment or process of accommodation cannot be done. However, if the object is brought too close to the eye, the focal length cannot be adjusted to form the image on the retina. The focal length cannot be adjusted to form the image on the retina. Can I continue? Class, can I continue? Thus,
Yes.
thus, there is a minimum distance for the clear vision of an object. There is a minimum distance for the clear vision of an object. This distance is called the least distance of distinct vision. Thus, there is a minimum distance for the clear vision of an object. This distance is called the least distance of distinct vision. Shortened as LDDV. Least distance of distinct vision, LDDV, or this is also known as, or the near point. The near point. So the least distance of distinct vision, the near point, is the minimum distance for clear vision of an object. So if you are asked to define near point, the near point, or LDDV, is the minimum distance for the clear vision of an object. Okay. Okay. For normal eye, this distance is generally taken to be, for normal eye, this distance is generally taken to be 25 centimeters from the eye. So this is an eye, the eyeball. The near point, if this is an object, the least distance of distinct vision must always be 25 centimeters from the eye. We measure it from the eye. We measure it from the eyeball. So it's 25 centimeters from the eye. Now, I said that as we grow, this distance recedes. We'll be going back. So if you bring a test here, an image here, because this position is the LDDV, the minimum distance where an object can be seen clearly. If it goes inside, or if this distance, the distance from the eye, is anything less than 25, that is when you see reading of text and images become so blurry, difficult. Now, at this distance, we have maximum visual angle subtended on the eye. So at this distance of 25, the angle subtended on the eye is maximum, because I told you that if the object is far, it subtends small angle on the eye. So the moment we get to the near point or LDDV, maximum visual angle is subtended on the eye. That is why you see the object so distinctly, clearly. Okay, all the features can be seen. But when you go into any distance less than 25, even though the angle is increasing, but you can't read clearly. Please, is there any question before we continue with our notes? Is there any question? Mameya and Co.
No, please.
Arefua, Julian, Kelvin.
No, please.
All right.
Please, I don't have any question.
You are not paying attention, Mameya. All right. So,
Please, I'm paying attention.
okay. Let's write on visual angle. Let's write on visual angle. The visual angle is defined as, okay. Just write a subtitle visual angle, and then the size of an object, as sensed by us, senses. The size of an object as sensed by us is related to the size of the image. Is related to the size of the image formed on the retina. So the size of the object as sensed by us is related to the size of the image. This is the retina. So the size of the image formed on the retina. If the image formed on the retina is large, you will see the object to be large as well. So the size of an object as sensed by us is related to the size of the image formed on the retina. Now, the size of the image on the retina, the size of the image on the retina is roughly proportional to the angle subtended by the object on the eye. Subtended. So the size of the image on the retina is roughly proportional to the angle subtended by the object on the eye. This angle subtended on the eye is known as the visual angle. So this is the angle theta subtended on the eye. Okay. So this angle, which is created by the object, the size of the object on the eye, is what we are termed as the visual angle. So theta is equal to the visual angle. And the size of the image, is directly proportional to the visual angle subtended, visual angle theta. So if theta is large, the image would also be large. If theta is small, the image would also be small. Okay. So this angle is known as the visual angle. Now, so once the object gets to the near point, which is 25 centimeters from the eye, the visual angle theta is maximum. So let me also include that visual angle is maximum when when an object is at the near point, or at the LGDV, which is 25 centimeter from the eye. Now, anything less than 25 centimeter, the eyes cannot see clearly. Anything less than 25 centimeter, the eye cannot see clearly. So we cannot see a bacteria, virus. This is because, sorry, the visual angle subtended on our eyes by the object, bacteria, or virus is so small. If the angle is so small, we cannot have a larger image because the image formed on our eyes is directly proportional to the visual angle subtended on our eyes. So that is why we cannot see a bacteria. We cannot see a virus because the visual angle subtended by the object's virus on our eye, on the retina of the eye, very, very small. And so with our naked eye, even when the bacteria, the virus is brought to the near point, which produces a maximum visual angle, we still cannot see because this angle subtended on the retina is very, very small, and so we can't see it. Please, is there any question?
No, please.
So where the object is brought to the near point and we can't still see, or we can still examine the part very well, that is when we use an optical instrument. So if you want to see a bacteria, because when you are given that this is the specimen bacteria, even when it is at 25 centimeters from your eyes, you can see, okay, then you need an optical instrument, okay? And what does the optical instrument do? The optical instrument increases the visual angle on the eye so that you can see whatever object that is put in front of you. So that's just the function of the optical instrument. The optical instrument increases the visual angle on subtended on your eyes so that if it is increased, then the height, the size of the object will also be large because size of object is directly proportional to the angle subtended on the eye. So basically, optical instruments increases visual angle artificially so that there will be a proper viewing of an object. That's the function of an optical instrument. Mami, I ask your question. So let's add something. We got to this angle is known as the visual angle. Please, let's continue. Optical instruments are used to artificially increase the visual angle in order to improve the clarity. Optical instruments are used to artificially increase the visual angle in order to improve clarity. So optical instruments are used to artificially increase the visual angle in order to improve clarity. That's the function of optical instruments. So your binoculars, Julian, are you there? Your
Yes,
binoculars,
sir.
the microscope, the hand lens, the telescope is basically to improve, artificially increase, as at when it is used, it would improve or increase the visual angle on the retina of the eye in order to improve clarity. And so when you are given a cockroach to examine the part, draw and examine the parts, because your eye is limited, even when the object is at the near point, 25 centimeters from your eye, you use a hand or a magnifier. A magnifier is a simple microscope. Okay, a simple microscope. And then just vary the position of the hand lens. Then by using it, you can see the magnified object, image of the object. There you can clearly see the parts and draw. Then the use of compound microscope in the laboratory. Okay, you cannot see spirogyra. Okay, so whatever they think is spirogyra is stained, then it is seen under the microscope. Then the detailed parts of the object which cannot be seen by the naked eye can be seen. So all that the microscope, the hand lens, the telescope does is that it artificially increases the visual angle on the retina of the eye in order to bring a clear viewing of the object. Any question? Please ask question. Ask question. Elizabeth, Bridget, ask question. Kezia, ask question. Leslie, you are also here. Nana Kwabena, Michelle, Mami Yam. Hey, Leona, these days you don't talk. What's your secret? Leona, what's your secret? Okay, so let's write on the magnifying power of an optical instrument. What do we mean by the magnifying power? Magnifying power of an optical instrument. And after that, we'll go into this optical instrument one at a time, starting from simple magnifier, a simple microscope, the hand lens. Then we look at compound microscope and then the telescope. So the magnifying power of an optical instrument. So magnifying power optical instrument. Au revoir. Au revoir. Hello, au revoir. Or
Yes, please.
what did I say as the function of an optical instrument? What is its function? What's the function of an optical instrument? Oh, everyone said it all. Anybody to share the function of an optical instrument with us?
Please, we said optical instruments, they increase the. Okay.
Go ahead. Oh, who was saying it? Okay, Mamiya, go ahead. If your
It
hand
increases the visual angle,
is,
which is proportional to the size of the object.
you are right, but you are missing some key
Please,
adjectives.
Erefa.
All right, Michelle, your hand is up. Let's hear from Michelle.
These optical instruments are used to artificially increase the visual angle in order to improve clarity.
So they are used to artificially increase the visual angle. At the near point, visual angle is maximum, but it is small, and so we cannot see the object clearly. And so we use optical instruments to artificially increase this visual angle in order to improve clarity of the object we are seeing. So when we talk about the magnifying power of an optical instrument, okay, it is defined as the magnifying power is represented by capital M. It's represented by capital M. And it is defined as the factor. Please put it down. The magnifying power is defined as the factor by which the image on the retina can be enlarged by using the microscope or the telescope. Okay, the factor by which the image on the retina can be enlarged by using the microscope or the telescope. Okay, its function is to increase the visual angle artificially on the retina in order to improve clarity. So when we talk about the magnifying power of an optical instrument, we are looking at the factor by which this visual angle is enlarged on the retina by using either a microscope or a telescope. I hope it is understood. Hello.
Please,
Yes,
come
sir.
again.
We define the magnifying power of an optical instrument, whether microscope or telescope, as the factor by which the image on the retina can be enlarged by using a microscope or telescope. The factor by which the image on the retina, okay, can be enlarged by using the microscope or the telescope. So this is defined as the factor by which the image on the retina can be enlarged by using a microscope or telescope. And so we are only considering these two as the optical instrument. So by using a microscope or telescope, the factor by which the visual angle, which is initially small, even when the object is at D, the factor by which it can be enlarged artificially, okay, artificially by using a microscope or a telescope is what we define as the magnifying power. So we determine in exams you'll be asked to calculate for the magnifying power, okay, or power of magnification of some optical instruments. So we'll be looking at them one after the other and then calculate the magnifying power or derive a relation for determining their magnifying power. Julian, are you there?
Yes,
Help
sir.
me. Kweku. So let's begin with how to calculate the magnifying power of a microscope. So magnifying power M, capital M. Don't forget, when you use small letter m, it means linear magnification. So here we create a distinction by using m. This is giving us m for microscopes. So for microscopes or microscope, m is calculated as the visual angle formed by angle formed by the final image by using the lens or instrument. Here it refers to the microscope. Visual angle formed by the final image by using the lens divided by the visual angle subtended or formed by the object when kept at D, by the object when kept at the near point. The near point is also determined as a D. LDDV is what is shortened as D. So we'll pick it one after the other. We'll pick it for microscopes, and then when we finish looking at microscope, we look at telescope. I don't want to. So when you want to calculate the magnifying power, it is the visual angle formed by the final image by using the optical instrument divided by the visual angle subtended by the object when kept at the near point. Okay, let me explain this a little bit. You see, we just defined the magnifying power, okay, of an optical instrument as the factor by which the image on the retina can be enlarged by using a microscope or a telescope. Now, when the object is at the near point, we just saw that when the object is at the near point, the eye, when object is at the near point, it produces maximum angle. It subtends maximum angle on the retina, theta naught. But for some objects, such as smaller objects, when the object is at D, we still cannot see it clearly. The reason why we want to use an optical instrument in order to artificially increase this visual angle to see it clearly. So when the optical instrument, the microscope comes in, it will enlarge this angle. That is why if you are to calculate the magnifying power of the instrument used, it is the visual angle subtended by the final image by using the lens divided by the visual angle subtended by the object when it is kept at D. That will give us how much the angle has been enlarged. Please, class, are you okay with the meaning of the formula or the equation? Are we okay? So when it's at D, it will give us an angle. But this angle is not enough to give us a clearer view of the objects. Then we use an instrument. When the instrument comes in, it will artificially increase this angle. So if we want to know the magnifying power, okay, of the instrument, we divide the angle formed when the instrument is used by the angle when it is at D. That is it. So let's pick it. Let's go through the magnifying power of some instruments, and we'll begin with the simple microscope. Please, before I continue, if you have any question, Leslie and Co, ask before I continue. If you have any question bothering you, Mami, Calvin, Julian, Leslie.
Please, I still don't understand the formula.
And you were quiet. We are looking at the optical instrument. The function of it is to increase the visual angle. That's one. Okay, when the object is at D, it gives us maximum visual angle, but we still cannot see the object clearly. And so the need for us to use an optical instrument. Now, when this optical instrument comes in, its function is to artificially enlarge this angle so that we can have clarity of the object. Artificially enlarge this angle on the retina so that we can appreciate the objects well. So if you want to calculate the factor by which the visual angle is enlarged, we look at the angle formed when the device, the optical instrument, is used, divided by the angle formed when the object is at D. That will give us the magnifying power of the instrument. Mami, are you okay?
Yes, please.
So the magnifying power, capital M, has a unit as just times. Meaning that if you calculate M and you have maybe 5, then we said that M is equal to 5 times. All that we mean is that the visual angle has been enlarged 5 times. So this is the unit of magnifying power of an optical instrument. X times. It's been magnified 5 times, 2 times, and so forth. That is basically what it means. Now, gentlemen, if you have any question, ask before we move on to the simple microscope or the hand lens, and then calculate its visual angle. So we use the simple microscope, which is also the hand or the magnifier, to enlarge. Julian.
Sir, please, can your answer be gotten in decimal places?
Oh, it is always expressed to the nearest whole number. Okay, so if you have something like 1.9, you approximate it to 2, meaning the visual angle is enlarged 2 times. All right.
Then, if given a question, do you write the formula and everything, and then, like maybe WASI, for instance, do you write the entire formula of the magnification?
So if there is the need for me to calculate the magnifying power of maybe a microscope, in solving it, magnifying power M, magnifying power of microscope is given by, this is M is equal to visual angle formed by using the lens, in this case, the microscope, divided by visual angle formed when object is at D. D is also known as maybe 25 centimeters from the eye. So this is how you state your formula and then move on. Julian, are you answered?
Yes, sir.
Okay, so let's pick the simple microscope and then calculate for its magnifying power. The simple microscope, which is also known as the magnifier. And we have magnifiers. We use the hand lens or the simple microscope in JHS, where we were using it to enlarge, okay, the size of our hand and then all that. It's also known as a simple microscope. Now, how do we use the simple microscope? The simple microscope is also the same as the, what kind of lens is this? What kind of lens is this? Oh, class. Answer.
Convex.
Convex or hey, convex lens or hey, Julian and Co answer convex or
Converging lens.
converging lens. Don't waste time for on trivial knowledge. Okay, this is trivial. We've gone past it. So if you want to use The hand length. What name is given to the center of the lens? What name is given to the center of the lens?
Center of curvature.
Hey, it's not true. What name is given to the center of the lens?
Still center.
But you are still not clear with the center. It's optical center. You've forgotten. What do you do for? This is F1, the first principal focus. We have F2, which is the second principal focus. Please, why do we have F1 here, F2 here? Why? Julian, why do we have F1, first principal focus, second principal focus? What's the reason? Julian. Hey. Julian is quiet. Frida. Kezia, you also there. Isaac Carter. Elizabeth. Calvin. Crispin. Kweku. Treme. Leonard. We did this together. Leslie. Mame. Adjoa Yankson. And Michelle. Why do we have F1? Why do we have F2? Anybody? Anybody to answer? Hey. Charlie. Elizabeth.
Yes, please.
Why do we have F1? Why do we have F2?
I think because it has two lenses, so
And
each side has
two lenses. It's not true.
two.
You see, you've forgotten your terms. Because we have two refracting surfaces, this is biconvex. Eh? Elizabeth, are you okay?
Yes, please.
Because this is a biconvex lens. Okay, light can be incidented here or here. That's why we have this. Now, the hand lens. When you look at an object using a hand lens, what is the nature of the image form? When you use a simple microscope, hand lens, magnify, what is the nature of the image form? Mamiya.
The image is bigger than how it looks like in reality.
The terms be bigger. Use contextual words.
Okay. The image is magnified.
Exactly. The image is magnified and image is magnified, and once it's magnified, the image is what?
It appears bigger. It becomes closer.
Yeah. It's virtual.
Virtual.
So, you see, we are looking at the objects. This is the eye. The eye is here. The object is placed at the near point, which is 25 centimeters from the eye. We could not see the object clearly. Visual angle produced is theta naught. the image formed is not clear enough. So in order to improve clarity, we use a magnifier, simple microscope. Now, for the object to be magnified, okay, and when magnified, look at your hand, using hand lens to view your hand. Your hand becomes magnified. Once it's magnified, whatever you are seeing as magnified and it's a virtual thing. It's not really there, but that is what you appear to see. So where must the object be in order to give you such an object, such an image? Where do you think must be the position of your hand in order to see it magnified like that? Where should the object be? Anybody? Hey, application of what we learned. Oh, we are using a convex lens for the image to be magnified and virtual. Where must the object be for such an image to be formed? Julian.
At the near point.
The near point, this is your eye. When the object is at the near point, you cannot see it clearly. The reason why you are bringing in an optical instrument, which is a simple microscope. So when the simple microscope comes in, where must the object be for the image to be magnified? That's my question. For you to see well, to see the parts well. Yes, a reference, Elizabeth. The object must be between the optical center and the focal point. So for the object to be magnified, it must be here, between the optical center and F. Mamiya, Elizabeth, and Frida, true or false?
Very true.
We are applying what we've learned. This is about application of what we've learned. So for us to have such an image, the object must be between the optical center and the focal point. Okay. I can't verify. Oh, I think verify. I'm sure it will be a network problem from your end, though. The only problem I have here is the reflection of light. But because we are doing refraction, it's in order. Okay, so the whole idea is that the object is at D. If we can see it clearly, there's no need for the optical instrument, a simple microscope. But because we cannot see it so clearly and examine the parts, we bring in a hand lens or magnifier. Now, when it comes, you see, with your naked eye, when the object goes within, when the object distance is less than 25, that you can't see it because you've gone beyond the least distance of distinct vision or the near point, so you can't see it clearly. But when the optical instrument comes in, you can go within the near point and still you have a clearer view of the object. This is the advantage of the optical instrument over the naked eye. Okay, so how does this work out? The image, this is how the image will be formed. We've done it. So a ray of light parallel to the principal axis. After refraction, what happens? A ray of light parallel to the principal axis after refraction, what happens? Hey, Charlie, people have forgotten. Oh. A ray of light parallel to the principal axis after refraction passes through the principal focus. Then a ray of light passing through the optical center. What happens? A ray of light passing through the optical center, what happens? Hey, Mamiya and Co. A ray of light passing through the optical center. Goes undeviated. So look at these two refracted rays. They are widening up. So to form the image, the objects, the rays must be extended at the back. And where they appear to meet will be a large image of the objects. So when an observer looks through the magnifier, this is the observer's eye. The observer sees the image as this. Now, what is the visual angle? You see, from the optical center to the object, this is the object distance, u0. This is the height of the object, h0. Okay, so this becomes the visual angle, theta. Let me explain this. This becomes the visual angle theta, the same as this. So this is the angle which will be subtended on the eye of the observer. Observer near Wahi. The angle that will be subtended on his eyes when the lens is used will be this angle theta. Please, is it understood, class? Hello, is it understood? Hey,
Please come again.
after forming, are you okay with how the image is formed? We've done this under lines.
Yes, please.
Oh, now we want to look at the angle subtended on the eye, and the angle is formed from that. There's the object. Okay, there's the object distance when the lens is used. So from the optical center to the object becomes u, the object distance u, or u0. Okay, so the angle here, when you look at this small right angle triangle, the angle here is the visual angle subtended on the eyes of the observer. So this is theta, and by vertically opposite angle, this angle theta is the same as this. So it's like theta here and the same as whatever is here. So this is the angle subtended on the eyes of this person observing the image through the microscope. Julian, are you okay? Mami, are you okay?
Yes, please.
Yes, please.
So
Yes, please.
we want to calculate the magnifying power of this simple microscope. Pay attention. This is a bit technical, so you must be attentive. How did we define magnifying power? Capital M is given by the relation visual angle formed when lens is used divided by visual angle formed when object is at D, which is 25 centimeters from there. Okay, so we are going to calculate theta. The visual angle when lens is used is theta. The visual angle when the object is placed at the near point or 25 centimeters is theta naught. So in effect, this is equal to theta divided by theta naught. But we are going to pick what theta is. If we look at the diagram, what is theta? Now, we pick in optics or light, we take the angles to be small angles. So theta and theta naught are small angles for accurate approximation in light. So look at this angle. We have the object height h naught. The object distance from the optical center is u naught. This is the visual angle theta. If we take the tangent of this, because we have opposite and adjacent, tangent of the visual angle theta is equal to h naught over u naught. Okay, h naught over u naught. Now, because theta is a small angle, in fact, in optics and then mathematics, and the optics in physics and then mathematics, whenever you take the sine, cosine, and then the tangent of small angles, the angle is approximately the result is approximately equal to the angle. So tan of theta, tan of theta, sine of theta, and cosine of theta. When theta is a small angle, the tangent of the angle is approximately equal to the angle. The sine of the angle is approximately equal to the angle. The cosine of an angle is approximately equal. So because tan, theta and theta naught are small angles, whenever you take the tan of it, it's approximately equal to the angle. Usually 5 radians, 6 radian, 5, 6 radian are small angles. So when you take the tangent, the cosine, and then the sine of small angles in radian is approximately equal to the angle. And so what we see as tan theta will change to theta is equal to h naught over u naught. Okay, so this becomes the expression of the visual angle when the optical instrument is used. Let's come to the visual angle when the object is placed at the near point, 25 centimeters from the eye. Please, are you with me? Are you with me?
Yes, please.
All right. So let's look for theta naught. We found theta. What about theta naught? The same method when we take tan of this angle, tan of theta naught is equal to the opposite, which is h naught over the adjacent, which is either d or 25 centimeters. please, 25 centimeter is represented as D. So, because theta is small angle, tan of theta naught is approximately equal to theta naught. Therefore, we have theta naught to be equal to H naught over D. Now we found theta, we found theta naught. So let's substitute them into the visual angle equation. M, therefore, is equal to H is theta is H naught over U naught divided by visual angle from when object is at D, theta naught is also equal to H naught over D. This, when we simplify, will be equal to times D over H naught. H naught will cancel. And then the magnifying power of a simple microscope becomes D over the object's distance U naught. This in some books is also written as 25 centimeter divided by object distance U naught. This becomes the magnifying power of a simple microscope. Any question? Class, any question?
No, please.
Are you okay?
Yes, please.
Okay. We need to continue, but because of the technicality of this, we'll end it here and continue another time on this. Next Tuesday, we'll continue with heat. The next, I think, Wednesday, we'll still continue with heat. But I'll find another time to treat this, the optical instrument again. So today, due to the delicate and brain-working nature of this, please, I'll end here. But I beg you, spend time to go over all that we've done, okay? Because we'll continue on this, but I don't want you to forget this. So I'll give you another date where we'll continue with this, which will be different from our usual weekly meetings though. All right. So this is where we draw the curtains on today's meeting. Just go and review this for me, which will be looked at in another time. Good night to you all, and we shall continue coming Tuesday. In fact, bye-bye.
Bye. Good night.
Same to all of you.